Hi, thank you for sticking around post-lunch. As he said, my name is Maddie Stone, pronouns she and her. I am a security researcher on Google's Project Zero team as of 2 months ago. And before that, I was working on the Google Android security team doing malware reversing, leading teams that looked into OEM devices. And prior to that, I worked down the road at JHU APL for about 4 years. So the goal of this presentation is not just to talk about what was this big WhatsApp 0-day used by NSO back in May, because quite frankly, the bug is kind of boring. Instead, I thought for this audience, let's talk about tools and techniques of when these types of 0 days and vulnerabilities become public. What can we do to really understand them for the many different reasons that each of us in this room might want to analyze the bug, think about what the exploit might look like, and things like that. So the agenda, aka walking through the reverse engineering process, is first, what went public and what did we know about the bug? Then we're going to go through a review of 4 different patch diffing tooling that is available currently, and how did each of those stack up against a very well-scoped problem and application, versus a lot of times I personally see, a lot of theoretical papers out about tooling versus how do you use it out of the box when you need it? Next, we'll talk about when static analysis came in, what types of things to look for, what was the result in this cases, and finally getting into dynamic analysis with Frida. So, hope we have some fun. So what do we know about this CVE? Facebook published an advisory that told us it's a buffer overflow vulnerability in WhatsApp's voice over IP stack, which allowed remote code execution via a specially crafted series of RTC packets sent to a targeted phone number. So in terms of advisories, this actually provides us quite a few details of information. It helps scope where in WhatsApp you're looking for, exactly what type of vulnerability you may be patch diffing for, and things like that. Then that same day, Checkpoint Research came out with a short blog post, which, a few hours after the advisory, and in that, they highlighted 2 different size checks that they saw added in the new patched version of WhatsApp, which they believed could very likely be part of the vulnerability. So the first size check, which I will refer to as size check number 1 when we are sort of going through some of the patch diffing tooling comparisons, is, I know this is a little small, but it's in one of the RTCP handler functions, which lines up with a Facebook advisory, so that helped scope down probably their patch diffing process. And it's checking the length argument of the packet it's about to process. So again, goes with a buffer overflow type of fix. The next one is they found another size check called size check number 2, which had the same boundary for length, and it was doing a check that it would only do the following mem copy, which takes that length value if the length was less than hex 5CA. 8, sorry, not 8. So 2 size checks they found quickly that were added in the patched version of WhatsApp versus the vulnerable version of WhatsApp. And so that's where we're going to start our analysis. These slides will be up right after this talk, so if you're trying to follow along or practice or do some technique skills, here are the samples. Both of them are linked to their virus total submission and just version numbers if you're trying to figure out which ones I was looking at with addresses and stuff. So let's get into patch diffing tooling. Prior to joining Project Zero 2 months ago, I had been working in malware analysis versus vulnerability research, so I really hadn't been using any of the patch diffing tooling that was out there. So I put out a call on Twitter asking, what's your favorite binary diffing tools, patch diffing tools? And all of the responses only gave me 4 tools that people liked of everyone who responded. We had Darren Grimm, BinDiff, Diaphora, and Radare, aka the radiff to command line in Radare. So that's what we're going to look at. But specifically, what I wanted to figure out is, will these diffing tools highlight this change quickly and correctly? And so for a very well-scoped problem, because quite honestly, the few times I tried to run patch diffing or binary diffing tools previously, it gave me a lot of data that I didn't know what to do with. So I figured, let's have a well-scoped problem. So based on Checkpoint's research, I quickly found that the size check number 1 they referred to was in subroutine 51E34 in the patched version of WhatsApp, and the size check number 2 was in subroutine 52D0C in patched. So from here, what are those functions in the vulnerable versions? What actually was changed? Are there any other changes as well? Because Checkpoint had also put in their blog that these were the 2 changes that quickly stood out to us, but we didn't see everything, so there might be more. So let's start with Darren Grimm. It's been out for a while, and it still only runs on Windows. Its current support is not IDA 7.3, but is IDA 5.6. And it is open source, but it was last publicly updated in February 2017. So this actually nixed me testing it fully because I have Linux and Mac desktops that I have all my tooling setups for, but I don't really use Windows, and also I don't have an IDA 5.6 lying around. So that was the first one that I crossed off the list. Then I went to the OG, BinDiff. BinDiff was created by Zynamics, who was then acquired by Google. It's not open source. It doesn't have a lot of public releases, but they have updated it to work on IDA 7 point whatever. And so the way BinDiff works is it has this plugin that gives you native integration with IDA. Most of my reversing paths, as you'll see, do still use IDA, although I've been switching to Ghidra for some things more recently, but as of now, still lots of IDA. So once it finishes its analysis, you open it up in one database, you tell it the other database you'd like to compare it to, and then it will open 4 tabs in your IDA. And so it will tell you any matched functions, meaning even though they might be different, we're saying these 2 functions go together. It will tell you unmatched functions in the first database and any unmatched functions in the second database, as well as different statistics. For this case, you're going to always have a primary and a secondary one, and so it's just the order that you sort of open these and how it's doing the comparison. So I had the vuln database open and compared it for secondary to the patched one. So, for example, this is the functions that had the size check added in right before the memcopy. And so what you see, if you can get close, you can change, the colors are terrible, I'm sorry. So, yay, I have the magnifying next, is here, these are 2 gray boxes that don't exist over here, even though you probably can't see these colors now. And then there are 2 more boxes down here on the patched version that aren't in the vuln one. So when I magnify that, now you can see the gray a little better. Oh, you still can't tell the colors. Okay. Imagine with me that you can see all the colors. No.
It's on the big monitors.
Okay, so yeah, they're saying you can see the colors a little better on the other monitors. But the 2 smaller boxes, so not the big one or this big one, these 2 smaller ones are highlighted gray rather than yellow, meaning they were not found in the primary, aka the vulnerable database. And when you scroll in even more, right here is that size check of verifying whether or not the length is less than 5CA. So to me, I was actually very pleasantly surprised that in this whole function it highlighted these 2 important parts where there are size checks happening. Yeah, so to me that was a first win for BinDiff. Then we have the other function though, because remember there were 2 size checks added. And what was interesting about this is that, again, you can't really see the colors on here, but I'll highlight them, is that there are actually 2 sets of red clusters of blocks or boxes missing in the patched version that exist in the vulnerable. So this was a new find because what we knew about previously when we started this analysis was that WhatsApp had added 2 size checks in, but this clearly shows us that they actually took blocks of code out as well. So that's a great place to then begin static analysis once we get there. So overall, my review of BinDiff was the matching was pretty spot on for a lot of the cases. It showed me where the vulnerable functions were versus the function and addresses I knew were patched. The UI for highlighting changes when it's not being projected on a giant presentation is pretty good. Being able to see what's new, what's changed, and what's added. However, I don't know that it's very obvious in the whole listing of the matched functions, which look like this, but a lot longer, which ones are important. Because especially for something like this, we're currently analyzing the native library lib WhatsApp that exists in the WhatsApp APK. So I had already scoped it down to lib WhatsApp, which through open sources I knew was responsible for the voice over IP and RTCP handling. And there were still hundreds of matches that weren't quite 1.0, but were in that 98 to 85% match range, which that's just enough little tweaks to probably make it interesting. So that's one place that I didn't think BinDiff out of the box solved all the problems for us. They don't support the decompiler, which some of the other tools we will talk about do. The UI for these graph images that I'm showing is outside of IDA. That didn't bother me, but it is something to note. And what was really nice compared to some of the other tools is BinDiff did not get caught up in name changes, offset changes, things like that, which is very helpful because those aren't the types of changes we often care about. So the next one up was a new to me tool, Diaphora. It's open source, constantly maintained and supported. When I made these slides, it had been last updated 2 weeks ago. And it does have current support for IDA, so 7.1 through 7.3 is what they say they will provide support for. They're also currently developing Ghidra support, and their plan is to support Binary Ninja in the future after Ghidra is launched. So, like IDA, Diaphora runs, like BinDiff, Diaphora runs through IDA and creates a bunch of tabs. It's really nice because all you have to do is run a script. So you say load script file, and then you run the Diaphora script, and it gives you all this output. It does take quite a bit longer than IDA. For my two native libraries.so files, it took about 2.5 hours to run. But if you only really have to do it once, not too bad. So this is again an output. This was all of the partial matched functions. So unlike BinDiff, which grouped everything that they say is matched together in one, they separate out the complete 100% matches from partial matches. And again, though, a very long list. So what's great is here we find one of those size checks we were looking for. This is sub 5.2 DOC. The vuln is my name that was added to it. And this is the size check number 2, which is the size check prior to the mem copy. And it says it matched it from same rare constant. So you can see the different descriptions, and they have pretty good documentation to understand what they mean. This is then the flow chart that Diaphora creates right inside of IDA rather than separate. But I actually found this one a little more difficult to tell what's changed because they're actually highlighting things that's changed when some of just the offsets have changed. And that's why it's not so clear where is the size check that occurred. So you can see here, I highlighted it with a giant arrow to pointing to the actual size check. So the code in the 2 bottom boxes actually didn't change. They just changed some registers and offsets. Yet it's highlighted here. And so here's just a reminder of what BinDiff looked like as a comparison. Then we get to the other size check that we knew was added. And here Diaphora actually matches just the complete wrong function. And that becomes pretty obvious also when you open up the 2 graph views. It did highlight to you, though, that it believes it's an unreliable match. And the reason why they say it was a match was the same address and rare constant. So they weren't confident in it, but it's still disappointing that it couldn't find the right match to help us work off the bat. So for my take for this scoped problem, the matching wasn't that great. It tends to get thrown off by naming different offsets, things like that. It does have support for decompilation diffing, but if the decompilation uses any sort of different variable names, you know how decompilers do, or the order they set them up, it's very much a straight, string type of diff. So I didn't find the decompilation output very helpful. However, it's open source and currently maintained, and I think there's a lot to be said for that in our tooling sort of landscape and ecosystem right now. And I do know that they are open and want people to continue just to support and help grow them. And they want to support other tools like Vidra and Binary Ninja, which is also something important in our community right now. So then I got to Redair 2. Honestly, to me, I had never really worked with Redair. It just sort of is something that I keep hearing about, but I'm like, to be honest. But there were actually a lot of people on my Twitter thread who kept saying, we love Redair's diffing. So figured check it out. Here's the links. They actually have a really great book that has a lot of details in it. It's open source and currently developed, even more widely developed because the last commit was 2 hours prior to me making these slides. And there's very small text that Redair sort of talks about themselves with. But they also have the CLI tool Radiff2, which just people were raving about. So let's check it out. So Radiff2 has a lot of different capabilities built in. It's not just one, here's the diffing, now let's look at what UI you want. So the very first thing is Radiff2 is a pretty straight binary to binary comparison. So not that helpful because write down 52DO2, which I now highlighted in green. That's where one of the functions, 52DOC, is the one we care about, and it's just showing us a strip of binary and how those bytes change at the address 52D1C. So not great, but what else can it do? Oh yeah, and it resulted in 150,533 different diffs. So then I tried the next one. So if you use the -A and -C tags, when you're running it, it's going to do function analysis first, and then do a function-to-function comparison. And you also tell it which architecture you're running on, and things like that. So I ran this. It took 9.5 hours to run, which I can't imagine if you have multiple libraries, like you might find in an app, or something larger than the little libraries I was looking at. But this is the output. It gives you a function. If it's unnamed, it just does the FCN prefix, sort of like IDA's SUV. If it's named, it will put the name there, and then tells you is it matched, unmatched, new, things like that. Unfortunately, for both of the functions we care about, it says they're new. There were no matches in the library, which was disappointing. Sad. So overall, this was obviously one problem. I'm not trying to say across the board, these are how the tools stack up, but for me it was very interesting of how do these work out of the box. When you're not an expert in knowing all the secret customizations, all the different things like that, will they stand up to the goal you're trying to solve, especially when it's a very straightforward goal. So in the end, bindiff matched both the vuln and patch functions correctly for 2 out of 2. Diaphora did 1 out of 2. Redair did 0/2. Darren Grimm just runs on Windows, which makes me sad. And my take on whether it clearly showed me the changes I would likely care about, yes for bindiff, meh for Diaphora and the one function they checked correctly. Well, Redair can't do much if it didn't match. But none of them did I think it's minute 0. Facebook has just released the new patched version of WhatsApp. I have the vulnerable version. Will these quickly highlight to me the changes I want to review and highlight? Probably not, because all of them still came up with hundreds of options that they suggested, all sort of in the same priority, were important changes. So yeah, that's basically what I just said. I do think Diafra could probably be very strong tool, but just out of the box for this case didn't seem to work. So now I know what's the vulnerable function that matches up with these patched ones. I also now know that for one of these size checks where a checkpoint said, hey, a size check was added, there was also clusters of code removed thanks to bindiff. So now we get into our static analysis. Oh yeah, where we're at, we have the two size checks. We know the corresponding functions. Yeah, so I'm actually very interested in finding out what did WhatsApp remove, because this function is obviously important. They added a size check here. What is this? So this is a cutout of one of those clusters of code that was removed. And what it is it's actually the processing to allow burst packet processing for our TCP. So they actually, in this function, they removed all of their support for burst processing in the patched version and removed this recursive call to itself. So probably should have added that. This is a cutout of the code that I named calls vuln 51D30 because it calls the function that includes the vulnerable mem copy. And in it, they have a recursive call whenever they're trying to do burst packet processing. So that's really interesting and led to a lot of information of this is probably where exploitation took place, because when you're doing burst processing, including recursion in there, it leads to a lot of good signals for buffer overflows, especially if those can lead to RCEs in the customized packets it probably includes. So now what? We did some basic, we have a lot of things that look interesting, we have some facts, but what makes this an interesting bug? What do we want to know about the exploit? Each of us in this room may have different reasons of analyzing, but largely we'll want to know, okay, we know there's a buffer overflow, but what can we write? What can be done with it? Then you're likely thinking to yourself, to frame your static analysis, how do we exploit that then? And lastly, how do we trigger it? They said this can be done remotely by just calling a target phone, so there must be a way that this little bunch of code can be triggered. So these are all the thoughts that come into our head and helping us to frame and think through our static analysis. So yay, reversing. So just again, to set expectations, subroutines of interest were the function with the vulnerable mem copy in the vulnerable library was 52FOO, patched 52DOC, and then the other one with the other size check were those. And I just list them in case the slides stand by themselves too. And these, which we'll get to in a second, I had started reversing the ARM32 libraries, so that's why it's there. So let's look at this mem copy. They obviously added a size check right before this mem copy, and that length that they're checking is just passed into the function. So there's no checks in the vulnerable version, and they just do the straight mem copy. So when we're looking at the disassembly, it takes mem copy, which was arg0, which is a buffer pointer, and they go into offset 1F7A4. Then they have the pointer to the packet that they want to copy, and then the length, which was arg number 2 to this function. But what's interesting is right after the mem copy, hex 100 bytes after the start of their buffer where they copy to, then they write the length of what they copied. So it's clear that they always assumed that the amount of data they would be copying from the packet would be less than 100 in this case, because then they start writing other important values. So in the patched version, though, instead, first we'll have the, up at the very top in the first block, we have the size check where they're checking to make sure that length is less than 5C8. Then they do the mem copy down in the middle of this block. But this time, instead of writing the length to hex 100 bytes from the beginning of the packet copy, they do it at 5C8. So that also confirms the gut check that they didn't mean for the value in the vulnerable version or anything after that in the struct to be overwritten by the packet buffer. Because in the patched version, they ensure that these values are after the maximum length that that could be. So after that, after you start to see that, you're going to do a lot more static analysis. It's not that interesting, so that's why I'm focusing more on process than just walking you through step by step. And so then I started backtracking to understand what is the structure we're copying this data into. What besides the length can we overwrite, and are those values that are at the end of the struct after the buffer? What is the size of this buffer supposed to be? Because if it's actually shorter than the maximum amount we can copy, and when I say that, hold on. So the buffer space is embedded in a larger struct, and that's where the length comes in. So if the larger struct that includes the buffer we're writing to, not a pointer to the buffer, but the actual buffer, and we can overwrite the end of that struct, then we also potentially have the ability to overwrite the following struct in figuring out what that is. And so those are all of the things that inform the static analysis of what's next. What do I look for? What is still worthy of static reversing versus switching over to other tooling at this point. But let's back up a few steps to help inform where that static analysis should go. So WhatsApp uses an open source project called PJSIP for its video conferencing voice over IP implementation. Thanks to Natalie Silvanovich of Project Zero, I did not have to redo all of that learning because she has published a lot on this and other video conferencing and messaging solutions. So when I Google WhatsApp, you know, my teammate who's sitting next to me's blog post pops up and tells me, oh, it uses PJSIP. So WhatsApp did add additional customizations on top of this, but to answer those questions on the previous slide, I used a lot of PJSIP's implementation and some of our diffing tools to be able to find what are the structs that PJSIP at least defined for these common functions, and then do some matching to see what values and things like that are in the structures in WhatsApp. And so they did differ quite a bit, but at least that gives you the understanding of most often WhatsApp's changes were at the end of the struct, so I could usually figure out what the members were at the beginning and stuff like that. They also used a lot of the same strings for logging, so that makes it a lot easier too. So after we start to do that static reversing, figure out what we can overwrite, then the thoughts become, well, how do we exploit it? We have a buffer overflow. What does that mean? What can we do with it? And so based on the differences, the removal of the burst packet processing from the vulnerable to the patching and the way that burst processing works when you dive into the implementation, that is very likely the easiest way to exploit this bug and really overrun that buffer. And also what was interesting is that the values in addition to the length that are in the struct after the end of the buffer are all related to burst processing in the vulnerable ones. So you can continue to change those as you continue to process each burst packet. And then we get into how do we trigger it? And that really gets into what path calls this vulnerable mem copy that we care so much about. And so I started like every reverse engineer with pressing Control X and then creating the graph to what I cared about, but it stopped very quickly. And this function I named is not an exported function. So there is not a clear way that it can get called, because remember this is a library, not a standalone executable. There must be a way for something external, aka the WhatsApp app, to call and cause this path. And so when I look at this top node and do a Control X on it, what I see is there are no call references, just data references in IDA. And so that means that its address is being saved to a spot in memory, but nothing is directly saying a branch and link or a branch or a call to this function. This is where we can see it saved. It's just straight up saved onto the stack as a simple variable. And so this gets a little complex. So that's when I decided to switch from our static analysis to dynamic analysis. And in this case, Frida, which we've heard, I think, its name mentioned in every single talk so far today, so there it goes. So how to set up and get this and get that information using Frida. So we've mentioned it a lot, but just to level set, what is Frida? It's a dynamic instrumentation framework. It runs on just about all platforms, actively developed, open source. So if you're trying to analyze an Android app, then the way that this works is, the easiest way to make it work is if you have a rooted Android device and you run the Frida server just on the Android device in the background, and then on your desktop or laptop or whatever analysis machine, you can then write combo Python JavaScript scripts to hook into and instrument the application or targets that are running on the Android app. So this is my setup. Pixel 2 running a user debug, which aka means you can get root. Android 9 build. I have a Verizon test sim because one of the frustrations and what makes Natalie Silvanovich a saint for doing all of this type of analysis is that, you know, when you're working with messaging platforms and things like that, you usually need SIMs and for it to authenticate correctly with servers, stuff like that. And then I was injecting the scripts into the Frida server from both, I did it on a Mac and Linux. The reason why I was running 9 is originally Frida didn't work on Android 10, but thankfully due to its active community, they immediately a day later got that fixed. So I installed the vulnerable version of the WhatsApp app on my device. And oh joy, they won't let me run it. They say it needs to be updated. You can't, it's way too old. How to proceed. So these are all the instructions it required to get the old WhatsApp to run. So first what I had to do was install the current version of WhatsApp. And with that, I registered the app, did the authentication with my SIM card to get the number, and then I force quit the app. You want it quit fully. So then, using ADB, I saved off the contents of the data/data app directory, because that's where all of that authentication and registration will be stored. So that I saved to the other machine. I then fully uninstalled WhatsApp and disconnected the phone from both Wi-Fi and cellular, and then changed the date to a date that was prior to the date. So I changed it to June 10th, since they told me that this app can only run prior to June 24th. And you gotta make sure that, you know, auto date changing and all of that stuff is turned off, and that's why I also had to disconnect from Wi-Fi and cellular. So then, using ADB, I installed my vulnerable version of the app back onto the device. And then using ADB, and one of the reasons you need a rooted device is I wanted to copy the saved off files back into the new data/data directory and overwrote all the files there. Then you start up the app still with Wi-Fi and cellular off. And if it starts up correctly, then you can turn on Wi-Fi to do the Wi-Fi calls and Wi-Fi messaging and stuff like that, but do not ever turn on cellular, or else you will have to go through this again. Because turns out cellular will override your automatic date and time settings and update it anyways. So now, after running through these steps about 6 different times, we could hook the functions of interest. So when I say functions of interest, I basically mean the 3 that were in our little call graph, because I wanted to know, those are the 3 that I know are of interest to me. That's the path I know about thus far. So I want to record off their arguments and who calls them to get a better understanding of when and where they occur in the landscape. But it's not as straightforward as some of the tutorials that exist out there for Frida, because most of the time with an Android app, you're interested in Java, because most Android apps are written in Java, but this is a native library. And then for the tutorials that do exist for native libraries, most of the time you're interested in the Java native interface functions, because those are the ones that are called from the Android apps. But in this case, the 3 functions we were interested in weren't JNI or exported functions. So instead, we need to find a way by using offsets to get Frida to hook those rather than by using names. So, for example, if the function had been exported, we would have been able to use the module.findExportByName function to automatically get the pointer and have Frida hook it. But instead, we need to get the base address of where this library is loaded into memory, and then add the offsets to that address in order to get the correct pointer. So this is what it ended up looking like. First, we're going to get the base address of where libwhatsapp.so is loaded into memory. And this is just an example of what it would look like if you are interested in a named exported function. You can instead just do this straight up. But we couldn't. So we added our offsets that we were interested in to the lib base address. One thing to note, you have to use the .add method instead of the addition operator, because otherwise it thinks it's strings and will concatenate the two together. So you need to use add, sub, things like that for any arithmetic operations you're interested in. You may also notice that these offsets are different than what I have been talking about before. So real life, I didn't think about it when I started my static analysis that I started analyzing the ARM32 versions of the libraries. Most modern devices all run ARM64. So I originally had put all the ARM32 offsets in there, couldn't understand why it was hooking totally different things. Then ding, 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 duh, it's running a different processor. So just went, looked it up, and quickly found the offsets in ARM64 lib. So this is what the first thing outputs when we run it. You know, it's going to be different since they're dynamically loaded each time you run, but we get libwhatsapp.so's base address is that. I was printing JNI on load to make sure that it matched the offset that I was looking for in my IDA database, and then I can get the 3 different functions we're interested in. We have vuln, calls vuln, and calls vuln. So how do we help them now to get this information? Thankfully, Frida makes it pretty straightforward. We're going to use interceptor to say, hey, that address I just calculated, so now that's what I want to hook. And we want to do these behaviors that I'm logging right here on our entrance to the function. If there were things we wanted to do on exit, such as change the return value, we would just do on exit instead of on enter. So what I'm saying here is I want you to log whenever I enter this function, get the return address, which thankfully Frida makes available through an API. And because it's offsets and I'm looking at my IDA database at the offset rather than the memory address as it's loaded in memory, I'm just going to subtract the base address so I don't have to do math separately. And again, using .sub rather than the subtraction operator. And then for the actual vulnerable memcopy function, I printed out a lot more because that was the pointer to our buffer where we would do the write to the contents of the packet that we could see, as well as the link that was being passed in. So this gives me a good ground truth of how does this operate in the good state before we try to exploit it. One of the nice things is Frida also has this hex dump argument, which meant just in line I could still not just print the pointer address, but the actual contents of the pointer. So this is what I found, is that while a call is ringing to my device, it keeps repeating the in calls vuln over and over. And after we answered the call was when it triggered the vulnerable method. So now I have a lot of good information, which can then feed back into our static analysis, because now I have the address of exactly where is that calls vuln, which was their stopping point before, where is it called from? And this is important. I feel like I missed a slide when I was supposed to tell you about this before, but okay, we're there. So the reason why the in calls vuln stopped, and one of the important parts of knowing PJSIP was that one of the main sort of structural things of how PJSIP and other RTC libraries work is they use a lot of callbacks. So it was saving everything to a callback table. But there are lots of different places that use callbacks and decide which callback table they want. So now we have the address to find where is it actually being called from. And with that, you go back through your normal static analysis processes, trace it back. You'll find a JNI exported method that can then be called, that is triggered by the app during normal calls. And where do you go from here? So I hope that I've given you lots of different techniques and ideas and thoughts of going into when you're trying to analyze one of these recently released 0 days or vulnerabilities. But you have a couple different options. The first thing I continue to do after this is continue instrumenting with Frida the vulnerable functions and path you're interested in. So that included beginning to, instead of copying the packet that WhatsApp thought it should copy, I replaced that using Frida with much larger, much more random data to see, can I at least get some crashes? Or what other values of importance began to change? That then leads into beginning to hypothesize and more formalize what you believe this exploit looks like. So once you fully understand the vulnerability and its capabilities, what makes the most sense for exploiting it and what are the goals? We know that Facebook said it's an RCE, so you're probably not looking for, you're probably looking to overwrite at some point a function pointer rather than corrupting memory to get kernel rewrite or things like that. And you're trying to also understand what can I as an attacker control from the other side of the WhatsApp servers. This gets to be a little harder because WhatsApp did say they made changes to their servers after the release of this vulnerability. And so that's why I use the word hypothesize versus creating the exact copy. Because what we also heard is that these functions were triggered prior to the user ever having to answer the call. That's what open source media said. Whereas I just said in the testing, it was clearly, parts of it only happened after. So that's something to keep in mind when you're doing these types of changes. And lastly, I think one of the most important things we can do as a community whenever there is in the wild 0 days used is doing the variant analysis. Because when you're finding a bug or a vulnerability, you're almost always finding more than one. And that's the same whether you're on the blue side or defense side or you're on the offensive side. But to use the 0 day in the wild, you usually only use one at a time. So doing that variant analysis to understand what other patterns, what other bugs are likely the attacker is holding on to then be able to block, burn, etc. And with that, I hope it was somewhat interesting, informative, and know a little different, not talking straight up about the bug, because I figure anyone can go and read, and the buffer overflow is really not that interesting. But instead, how can we apply this and continue growing our tools to do these types of analysis quickly to hopefully help protect people? So some really random thoughts, but I do think we still have a ways to go with our binary diffing and patch diffing tooling capabilities. Nothing out of the box is able to highlight to you those big changes like a size check added versus some of the other changes that were highlighted. But also, sometimes it does take getting into a committed relationship with your tools so that you can really begin to understand each of their intricacies and customizations that allow them to be that much more powerful than out of the box. So setting up our tooling sets prior to needing them and getting to know them well. I love static analysis, and if you've ever seen any of my previous talks, I almost always strongly defend my reasons for doing static analysis and not dynamic analysis. But it would have taken me so much longer to stick with static analysis and not switch to Frida. It took me maybe an hour and a half after I got WhatsApp installed on the phone. We're going to consider that separate. An hour and a half to get all of that data, Frida installed, things like that, and get the data I needed versus how many hours of combing through all the different callback calls to find what it's called. Yeah, so with that, Thank you, and are there any questions? I do not. If anyone's in Checkpoint and wants to tell us, that's cool.
How they found it so quickly, like with all the diffs, like did they zone in because of the CVE details, or?
I don't know because I did not talk to them, but I would guess is that the CVE details in the Facebook advisory were very clear in that it's a part of the RTCP handling in the voice over IP stack. So my guess would be is that if I was to do this over again, now knowing, because I didn't fully know what those details meant to me at the moment when I read it, honestly, is that go ahead and do dynamic analysis first to see what sort of function path happens on a call, since we knew that from some of the reporting is that this was occurring on people's devices from a call that didn't have to be answered, is do that, get that call stack trace, and then see what functions are also in the diff and localize by that. And also using some of the intricacies, like I didn't show you, but in the screenshot of BinDiff, it can tell you if there's instruction change versus jump changes versus graphical structure changes. And so using some of that details to further localize and stuff like that. Yeah, I definitely spent way too long in static analysis, banging my head against the PJ-SIP libraries and trying to find what all these structures probably were, who was calling them, what was the format of the callback tables, and hypothesizing which functions fit in where. Whereas I said it took me maybe 90 minutes as soon as I hit up dynamic analysis. I also think if I did further customizations with the tools and had them installed easier, because although BinDiff was gave me the greatest results, I kind of moved away from it at the beginning and went to others first because I couldn't figure out how to get it installed correctly, and the IDA plugin button to show up the way it was supposed to. Because the one thing about BinDiff is although it has been updated, its documentation has not been updated. Any other questions? Cool, well thank you so much.